going to talk about Stokes Theorem. And first of all, just a general, so what Stokes Theorem does is it relates the line integral around a curve to the surface integral, okay, but this is dealing with a vector field where you're integrating, so the integral of the curl around the area, around the surface of the object, is equal to the integral of the vector field dot with the dr around the outside. Okay, so let me try to give you an idea of why that's the case, and then we'll come back and talk about this picture. So let's look at, so I've drawn a couple of different surfaces here. Well, the same surface, but with different vector fields, F. Okay, so in this one, the vectors, okay, so they appear that they're coming out of it, but what I meant is for these vectors to be in this surface. Okay, that's what I meant for them to be, but it's kind of hard to draw that. So imagine, so you've got this surface right here. These vectors are just pointing, they're parallel to the surface. They're on the surface, not coming out of it. Okay, so just think of it that way. Okay, so what's going to happen? Let's examine this first. Okay, what's going to happen? So what that is going to be is you're going to maybe start right there, and then you're going to go around the boundary of the surface. Okay, so you're just going around the boundary. You're just only taking the line integral around the boundary. Okay, and just a second, let me see if I can draw that better. You're only taking the line integral around the boundary. Okay, so you're only going around like that. So so that's what this part is right there. So that's F C F dot dr. So now what's happening is the your R is right here is going this direction, and your vectors are in the same direction as your R. Well, sort of. They're just so if you have two vectors right here and you take the dot product, okay, the dot product is going to be positive. Okay, if vectors are, if one's pointing this way and one's pointing that way, then it's going to be negative. Okay, so if they're pointing in opposite directions, it's going to be negative. If they're pointing in the same direction, that's going to be positive. Okay, relatively in the same direction. If they're perpendicular to each other, then the dot product is going to be 0. Okay, that's the idea right there about dot product. So, and that's a dot product right there. Okay, as you're going over here, okay, so here your vectors along the curve are that way, and then this is this way. So that's still going to be positive. Okay, but as you come this way, then they're negative, and it's going to be negative. So what goes along here is going to be similar to what goes along that, but negative. And then these are going to be negative, okay? So in this case, for this one, this line integral is going to be roughly 0 because the positives and the negatives cancel each other off. Okay, now, if we look at this one instead, we look at that one now, this surface here, and you're taking the line integral around the whole thing, then here the direction going along the curve is roughly the same, is really close, is in the same direction roughly as these vectors here. So that's going to be positive. And then the same thing as you come along here, these are going to give you positive. And as you go along this way, okay, that's going to be positive too. And as you go this way, these are pointing roughly in the same direction, so that's going to be positive. So here, the integral is going to be positive. Okay, now, if you look at what's going inside, okay, so if you look at, so imagine if these are currents, and if you place and maybe that's this is the top of maybe this is the surface of some water, okay, running down a stream or something or somewhere. You place a stick right here in the water, what's going to happen? Well, you have some things pointing here, but then you've got some currents going this way. So the stick's going to get pushed that way, but it's going to get pushed this way, and then, but then the stick's going to start to spin. So if you put it like almost anywhere, you put a stick almost anywhere, then the motion is going to for it to start spinning. If you put it right here, then these are going to hit it and start spinning. Okay. So that's then it's going to spin in the counterclockwise direction, which is the positive direction. Okay, so the spinning is the curl. If you put the stick right here, and this one, it's not gonna spin. It's just gonna go off it's just gonna move that way, right? If you put it like that, it's just gonna move that way. So overall, it's just gonna like not spin. Stuff's not gonna spin. Here, it's spinning in the positive direction. So this is giving you an idea of why these two can be equal, okay, and then been proven to be equal. Okay, now one last thing. I want to talk about this a little bit, and that's the orientation. Okay, and it turns out that I've been teaching you wrong because I said that you can swap X's and Z's as long as you swap the I and the K. Okay, so that turns out to be, well, actually, I'm not sure about that one, but I do know that this one's wrong. If you swap the Y and the Z and you swap the J and the K, then it doesn't, you're gonna mess up a sign somewhere, a negative. It's gonna mess up a negative sign. So this cannot, so I taught you before that you can do that, but no, you can't. And I'll get to a problem in a little bit that kind of shows why that's the case. Well, if you were to do it the other way, then it would not work out. Okay, but anyways, so I'm sorry I taught you the wrong way. I don't think it made much of a difference. And as far as applying it, you always choose your orientation, where you're going to put stuff, and so you can always choose it to be the Z being the up direction. Okay, so anyways, so here we have a surface here. This is from the textbook, and you have there's two orientations for the surface. One of them is with the normals pointing up, pointing this way, up, and the other one is pointing the opposite way, pointing down, which would be look like down in this case. Okay. When you're in another situation, then it might look different. But here, the normals appear to be going up, but then there's also another orientation which is down. Okay. So so essentially, if this is the up, so the Z direction is the up, is the top of if this is the top of this surface would be, so there's a guy walking right here, you can kind of see that, right? So the top would be, if the guy were to look up, that would be the top. So this is the top, and then the bottom is underneath, okay, in this case. So so if the top of the surface is up here, then if the guy's walking around the outside, then his head points in the same direction as what the top is supposed to be, or the outward is supposed to be. Okay. And if that's the case, then the surface is to the left of this guy at all times. Okay, his left. As he walks around, the surface is to his left. Okay, and that is the positive orientation. Okay, if you're walking the other direction, then it's the negative orientation. It's also counterclockwise. Counterclockwise. Okay, so this is, so in this case, right, and when these two, right, this one particular, we'll do both of these. You're looking at the flux going up, or the curl going up. Okay, in both of these cases. So great, let's get to some problems. Maybe one more thing that I should mention before the problems. And that is, well, a lot of times, some of these problems are going to deal, I'll just mention this now, and then when we get to the problems, then you'll see better. But some of the objects that we're looking at in the problems involve oh, wait, no, that's something else. Let's just go to the problems, okay? Okay. So we got number 1, first of all, and you're supposed to evaluate the curl across the surface, okay? There's 2 ways you can apply this theorem. One of them is if you're given this, if you want to find this one, you can use this to find it. Another one is if you want to find this, you can use that to find it. And sometimes this is easier to find, sometimes that's easier to find. So you're going to do both of them. So in this case, they want us to find the curl across the dot ds, across the surface. Okay, and so we know that that's equal to the integral of at f dot dr. Okay, so it's going to be a line integral. Okay, so let's take a look at what's the surface that we have here. Well, it's a hemisphere, y greater than or equal to 0, oriented in the direction of the positive y-axis. Okay, so let me draw a picture here. Here we have the z-axis, and here we have the y-axis, and then here we have the x. And you have x squared plus y squared plus z squared equals 4. So that means that the radius is 2, right? And so this is going to come out to 2. And that's going to come up to 2. And that's also coming up to 2. And let me just draw we're going to extend the x-axis and extend the y-axis down. That's also going to come out to 2, and that's also going to come out to 2. Okay, so essentially, you have the surface of this sphere here, something like that. Okay, so you have this sphere coming out this way. Now, what we need to do is find, so you have this is your surface out here, right? The boundary of that surface, because it says y greater than or equal to 0, the boundary of the surface is going to be this part right here, this circle here. Okay, so boundary of S is x squared plus z squared equals 4. Okay, so so basically you just set y equal to 0, and then that gives you this. That gives you the boundary. Okay. So, and we can parameterize that. by, now in the past I said you can just swap the x and the, I'm sorry, the z and the y. Okay, but that turns out that I was telling you that doesn't work, so that's really not good of me to have done that. But what you can do is, so if you look at it like this is the positive x direction, that's the positive y direction, right? I mean the positive z direction. And so if you look at it, if you kind of rotate this x around, this positive x, rotate that around, then the z stays going up like that. Then x is still going to be the place of our cosine t. I mean, I'm sorry, not sorry, I'm sorry, 2. Hold on a second. Okay, so first of all, we need to get the orientation correct, okay? So should we be going this way around the circle, or should we be going that way around the circle? Let's get that correct first, and then we'll proceed with how to do the next part. Okay, so coming out this way, going towards the y-axis, that's the positive direction, right? So someone walking around it, that should be to the left. So that means we got to go. That means we should be going this direction around the circle. Okay, usually we're going that direction. So from z to x, and if you set it up like this, this is going from x to z as you go counterclockwise. That's going from x to z. So what we need is the z here and the x here. You need to go from z to x, from z to x. Okay, and then we want that to be the counterclockwise direction. So that means that x takes that means x takes the function of y, or 2 sine t. Okay, and z takes the function of your kind of x in that case, so 2 cosine t, and then y is 0. Okay, so that's why you can't just swap the x and y, because you have to worry about which way it's oriented. Okay, so 2 sine t, 0, and 2 cosine t. So that was the parameterization. So remember, to take the line integral, you need to find the parameterization, right? Our parameterization. Now it's f dot dr, so what we're going to do is we're going to find r prime of t, which is 2 cosine t, 0, negative 2 sine t, like that. Okay, meanwhile, okay, so you've made these substitutions here. So meanwhile, let's go work on this for a little bit. Okay, so f of r of t. Okay, so everywhere that you see a z, then you want to change it to 2 cosine t. So that z becomes 2 cosine t. And y is 0, so that becomes just either 0 or 1, okay, in the I direction. But instead of doing that one, I'm going to just go with the other notation. So that's the I direction right there. Then right here, this x, that becomes 2 sine t. Cosine y is cosine of 0, so that becomes just another 1. And then over here we have x times z, so that's this times that, so that's going to be 4 sine t cosine t, but then with sine of 0, so that's all going to be 0. Okay. So that means our f of r of t is 2 cosine t comma 2 sine t, comma 0. And then we're integrating f dot dr. So that means that we're going to take the dot product of this vector with that vector, the r prime. Okay, so that's this times this, which is 4 cosine squared t, plus this times this, that's 0, so that's great. And then that's 0 too, so that's great too. So that plus 0 plus 0. And another thing I forgot to mention over here was that for this parameterization, since we're going around all the way around the circle, then t is from 0 to 2 pi. Okay, so that means that the integral is equal to the integral from 0 to 2 pi of 4 cosine squared t dt. Okay, so that's 4 times 1/2 t plus 1/4 sine of 2t from 0 to 2 pi. Okay, so if you put 2 pi or 0 into here, that's going to be 0, and so you have 4 times 2 pi over 2, so that's 4 pi. Okay, so 4 pi should be the answer. Do you have any questions on that? Now, one interesting thing is that this one is the surface is this sphere out here, right? But if you were to like if you were to deform this surface, so it's still like continuous surface, but you just like so let's say this is a part of a balloon. If you were to deflate the balloon a bit, but still have this boundary, okay, so the surface has changed, but it still has this boundary, then the curl across the surface would still be, the integral would still be 4 pi. Would still be 4 pi. So that's kind of an interesting piece of information there about that. I'll probably mention that later. Okay, so that's using Stokes theorem this way. Let's do another example. So number 2. Okay, so what we have here is, again, we're going to apply Stokes theorem, which is this, f dot dr of this integral here. So the integral of curl across the surface. Now this surface is really weird. Let me attempt to make somewhat of a drawing of it. Maybe not the surface, but all we really need is the boundary of the surface. And this, it says the top and the four sides, not the bottoms of the cube, are vertices oriented outward. Okay, so let me attempt to draw this. So let's say this is Z right here going up. And then over here we have Y coming this way, and then we have X coming that way. Okay, so those are the coordinate axes. Now, your cube has vertices plus or minus 3, plus or minus 3, plus or minus 3. So that's 8 different vertices, which is what a cube has. So, and the vertices, if you come down, let's see, come down this way a little bit, and you come across, and then you go back that way, then that would be one vertex. So it's underneath the XY plane. This is underneath the XY plane. So this is down. And maybe the coordinates here would be, okay, so the X direction is it's -3, because here this is positive X coming this way, but it's back there. The Y direction is +3, and the Z direction is -3, right there. That would be one vertex. Coming this way would get you another vertex. Okay, and this one would be, the difference here would be that the X is positive also. Okay, so that's one, this is one part of the bottom of the cube. Okay, and then you'll have another one over here and another one over here. Okay, so this vertex here would be that one down there. Here, Y is also negative, so all of them are negative. And this one, the X is positive, but the Y is negative. Okay, so in all the vertexes, the Z's are negative. Okay. Let me draw that one here. I'll draw this one here, there. The backside I'll do with blue. Okay, so we have this one, and then we have this one, and we have C, and then on the backside we have D. So that's that. Now the cube comes up from there, comes up. So if you can imagine, this would be, can imagine a box with no top on it, but it's flipped upside down, and the box comes out like this. The box is above this. This is the opening of the box. Down here is the opening of the box, and the box is above it. So you're looking at this orientation going this way, counterclockwise around the box, the bottom of the box, or the lid of the box, or the top of the box, okay, which is in the box upside down. Okay, so the curl around the whole, around all, so this one right here, this curl, there are 1, 2, 3. There's 4 sides and the top of the box, and you're integrating. This is an integral over all of those. This represents integral over all of those pieces. Okay, and this integral over all those pieces, all those surfaces, is equal to this integral here, which is integral around this bottom part. Okay, and unfortunately, there's 4 line integrals that we have to look at. Okay, so first of all, let's look at the first line integral, so from here to here, and you can parameterize that with by this. So the Y and the Z part are both just, the Y part's 3 and the Z part's -3 throughout this line segment. The X part just goes from 3 to -3. So you can parameterize this with 3 minus 6t. Okay, so when t is 0, this is going to be 3. And when t is 1, it's -3. So when t is 0, it's 3. T is 1, it's -3. And then you just make y 3 and z -3. Like that. Okay, now f of r of t is going to be, okay, so what happened here is you would put a, 3 minus 16 for x. For y, you would put a negative, you'd put a 3, and for z, you would put a negative 3. Okay. Okay, then you would do the same thing for this and this. However, you're going to take the dot product of this vector with r prime. And we know r prime is just the derivative of this, so it's negative 6, 0, 0. I know it's 0, 0. So that means it doesn't really matter what these two are. We don't have to like try to figure that out. Because when we take the dot product, f dot dr, we're going to get this times this. Okay, so that's, I think that's nasty. So negative 6 times 3 times, negative 3 times 3 times all this, that turns out to be 162 times 1 minus 2t. Okay, so the A integral, this integral along this part of this integral along the A part is going to be integral from 0 to 1, because that's 0 to 1, of 162 times 1 minus 2t. Okay, and that, when you integrate that, you have a t minus t squared. Okay, that integrates to t, that integrates to t squared. And you're going from 0 to 1. If you plug a 1 in, you get 1 minus 1, so that's 0. If you plug in a 0 in, you also get 0, so that's going to be 0. Okay, now I want to, so this is A, B, what? Why did I label that C? Why did I label that D? Oh, that's weird. Because it seems like it should be A, B, C, D, but I labeled it D. Oh, I can't believe I did that. Okay, so D, when you do the D integral, your R of T is also going to be your R of T when you do the D integral. Okay, so here you're going from negative 3, negative 3, negative 3 to 3, negative 3, negative 3. So the R integral is going to be, the X component is going to be negative 3 plus 6t. Okay, and then that way when t is 0, you get negative 3. That's negative 3 when t is 0. And when t is 1, you're going to get negative 3 plus 6, which is 3. And then these two are negative 3 and negative 3. And your F part will be x, y, z. And x, y, z is similar. So here's your x and your y, z. So this is the same thing right here. If you factor a negative 3 out, you get 1 plus 2t. Wait, I'm sorry, you get 1 minus 2t. Okay, like you did here. And when you integrate that from 0 to 1, it's going to be also going to be 0. So the A integral is 0 and the D integral is 0. So that and that are both 0. Okay, now, if we look at the B integral, and like I said, these two parts are going to be 0 when you take the derivative, so that's why how that works out. So we're just going to get this multiplied by some constant, and then that's going to just end up like that. Okay. Okay, now let's look at the B integral. So here you're going from negative 3, negative 3 to negative 3, negative 2, negative 3. So this is only the y one that changes. Okay, so the x one is negative 3, The y one, you're going from 3 to -3. So that's going to be 3 minus 6t. So when t is 0, this is 3. When t is 1, this is -3. And then the last one is -3. Now your f of r of t, again, it doesn't really matter what the first one is. So only concerned about this one, x times y times j. So x is -3 from here. This is x. Y is this one. And then again, it doesn't really matter what this is. Okay, because it's going to get dotted with 0. R prime of t is 0, -6, 0. Okay, and what's going to happen if we continue these calculations further? Then you're going to have something times 1 minus 2t, and that integral is also going to be 0. And then likewise, c is going to give you 0. Okay, and so you add these up together, and you get your answer, which is 0.
I hate those questions.
Yeah. You have a question?
Oh no, I was saying I hate when the answers come out to be 0.
Oh, yeah.
And then you think you can do that on the test.
Well, it's nice because if you're going to guess then and you guess 0 or guess 2 pi, then maybe you luckily get it right. But then it's like, well, okay, you don't feel like you don't feel good afterwards probably though. Maybe you do feel good. I don't know. So that's using Stokes Theorem to find this by finding this instead. Because this would be pretty hard because there's like a whole bunch of surfaces and you'd have to parameterize each of those surfaces. It could be messy. And you'd have to calculate the curl as well. Okay, so let's look at the opposite way. Number 3, use Stokes Theorem to evaluate a line integral. Okay, so you're going to use it to evaluate a line integral, where c is oriented counterclockwise as viewed from above. C is the triangle with vertices 3, 0, 0, 0, 3, 0, and 0, 0, 3. Okay, so let me draw that over here. Okay, so 3, 0, 0 would be right here. 0, 3, 0 would be over here. And 0, 0, 3 would be up here. Okay, so this is the triangle right here. And so we're supposed to find the integral around this curve. Okay, so start here maybe, go this way, go along that one, come up there, and down there. That's what we're supposed to find. However, we're supposed to use Stokes Theorem, so that means that we're going to evaluate this one instead, the curl of f dot ds. So the surface would be this surface right here. Okay. So one way that you can calculate the curl is you can use the formula certainly, but another way you can do it is you can set it up as a determinant. Okay, so this would be below the I, I'm going to put ddx. Below the j, I'm going to put ddy. And below the k, I'm going to put ddz. And then I'm going to put the components from the vector field underneath. So x plus y squared, y plus z squared, and z plus x squared, those three. And then copy it down over here. Okay, and then to calculate it, I would do like a determinant. So this times that, but really rather than times, I would apply this to this. So the partial of this with respect to y, that's going to be 0. And then subtract the partial of this with respect to z. So here's the I, so you're looking at that, which is going to be 2z, minus 2z. Okay, and then the next one would be the j's. The partial of this with respect to z, that's 0, minus the partial of this with respect to x, which is 2x. And then the third component was the partial of this with respect to x, which is 0, minus the partial of this with respect to y, so 2y. Okay, so the curl is negative 2z, negative 2x, negative 2y. Okay, now, here, so we have to go back to what we learned about surface integrals. And essentially, what I'm going to do is we're going to integrate over this region here because we can write, okay, the actual triangular surface is part of a plane. Okay, it's part of the plane, z equals 3 minus x minus y. Or which came from x plus y plus z equals 3, right? Because these all come out to 3s, right? These all come out to 3. So that's the surface of the plane. So I'm going to use that right there. Okay, and plugging this in for z. Okay, so I have a negative 2z. So I multiply everything here by negative 2. So that's negative 6 plus 2x plus 2y. Okay, that will be my exponents. And then just leave those two alone, negative 2x and negative 2y.
Professor Hurst, I don't think your audio's on right now.
Oh, no. Really? You can't hear me now?
I can hear you.
Oh, strange. What about now? Can you hear me now? Dang, maybe something.
So I can hear you fine.
Yeah, okay, just a second. Let me touch something. Okay, sorry about that. Okay, so anyways, okay, so let's see where we're. Okay, so this right here is this z equals 3 minus xy is the area, is the equation for this plane that includes the triangle. Okay, and so in the flux I substituted in for the z, and what we're going to do is we're going to use this formula right here. We're going to use that formula there, and in that one, this is our P, and this is our Q, and this is our R for that one. And what that one is we're going to integrate across this surface down here, across this projected down into the XY plane. Okay, and so that looks like, if it's the XY plane, that is this. This is y equals 3 minus x. Okay, so we're integrating over that region there. Okay, so what are the limits on, if we integrate in y first, what are the limits?
Is it 0 to 3?
In the y. So if you do a vertical line here.
It's to the equation, so 0 to the equation.
Yes, 0 to 3 minus x. And then x goes from 0 to 3. Okay, now we have negative p zx. Okay, let's see, zx is going to be negative 1, because you just take the partial of this direct x, and zy is also going to be negative 1. Okay, so we have negative p times negative 1. So it's basically just p. So all this okay, then we have minus q times zx, but this is negative 1, so it's basically just plus this one, which is actually minus 2x. Wait a minute, minus 2x? What? And then we have plus r, so that's minus 2y. Okay, and so, wow, this is nice. The 2x and that 2x cancel, and that cancels, and that cancels. Wow. Okay, so we have 0 to 3, and then this integrates to being negative 6y, and it's going from 0 to 3 minus x. And then you subtract, put a 0, and that's going to be 0. So it's negative 18 plus 6x evaluated dx. And so integrate that. It's negative 18x plus 3x squared from 0 to 1. Negative 18. Wait. How the? I somehow changed from going from 0 to 1. Well, magic. Okay, so it should be a 3 there, plus 3 times 3 squared. Negative 54 plus 27, so that's negative 27. Okay, great. Any questions on that one? So that's going back the other way. Let's do one more question, one more exercise. This would be number 4. The same thing as last one. Okay, so here's our vector field. And
Okay.
shut up, Siri. So here's our vector field. And then we're going around the boundary of the part of the paraboloid in the first octant. Okay, so let me go ahead and draw the region first. So this is the paraboloid. When x and y are 0, you're up here at 1. And when z and x are both 0, then y is going to be 1, so you're over here also. And then likewise, you're 1 right there. So it's something like this. Okay, so the part of the paraboloid in the first octant, C is the boundary of the part of paraboloid in the first octant. Okay, so this is your line integral goes around 3 different curves. So that would be challenging to calculate because it's across 3 different curves. So we're going to use we're going to use the flux over the surface. Okay, and again, this D surface is going to be down here. Okay, it's going to be this projecting down here because we have it as Z equals. So that's the route that we're going to go. Okay, so first of all, we want to calculate the curl. I'll do that up here. So the curl of F and your x is xy, yz, zx. Okay, so in the I direction, it's the partial of this respect to y, that's 0, minus the partial of this respect to z, so that's negative y. And then in the j direction, the second component, that's 0 this way, and minus that one, which is x. Z, minus z. And then the k component is the partial of this respect to x, which is 0, minus the partial of this respect to y, which is negative x, which is x. That's negative x. Okay. Now, meanwhile, over here, we have this equation there. So that's the equation that we're going to go with. Z equals 1 minus x squared minus y squared. And so the first thing we do is we plug this into here. Okay, so the curl now becomes negative y, and then we have negative z. So the negative of this, so that's negative 1 plus x squared plus y squared, and then the last component, negative x. Okay, so this is just plugging into here. to get the curl in terms of just x and y. Okay, now, when we project down here, let's see, what's that going to look like? What happens here is z becomes 0, so that becomes 0. So we have x squared plus y squared equals 1, right? And we're looking at this region right here. Okay, that's just making z equal to 0 here, making z equal to 0 here. We get that. Okay, so here z equals 0 gives you that, which is this boundary here in the xy plane, which is this part of the curve in the xy plane. Okay, but we're interested in integrating over this area. Okay, now let's set up this integral here. We'll set that up in an integral there. I'll just call it D for now. It's region D. But it is the curl. No, it is, I'm sorry, it's this right here. Okay, so this is P, and this is Q, and all this is R. Okay, we know that ZX is partial with respect to X, so it's negative 2X. ZY is negative 2Y. Okay, so this negative P, ZX, that would be this one. Negative P, so that would be positive, but then there's another negative there, so it's negative 2XY. So this times that times the negative, and you get negative 2XY. Okay, so that's from this one. This one, wow. Okay, this one right here is going to be minus 2y plus 2y times x squared plus y squared. Okay, so that's the 2y times all this, basically. So multiply that by 2y, and then multiply all this by 2y. I'm going to leave it like that, though. And then this last one will just be just itself. So I'll just take this minus x down. Okay, and that all that is dA. Okay, now what I'm going to do is I'm going to shift to polar coordinates. Okay, so I'm going to x equals r cosine theta, because I want to integrate across this here. So r cosine theta, and y is r sine theta, and r, to get this region right here, r goes from 0 to 1, and theta goes from 0 to 2 pi. So theta goes from 0 to 2 pi, r goes from 0 to 1. Wait, not 2 pi. I don't know what I'm thinking. I'm just saying stuff without thinking. Okay, what's this angle here? And straight up, that's 0. What's this one? Okay, that's pi over 2. Okay, so 0 to pi over 2. Okay, so r goes from 0 to 1, from 0 to 1. Theta goes from 0 to pi over 2. Okay, now I plug everything in. So plugging in r cosine theta for x and r sine theta for y, that right here gives us negative 2 r squared cosine theta sine theta. That's what that one is. This one is minus 2r sine theta. This one is plus 2r. This is r squared, and that's r cosine theta. I mean r sine theta. So this is going to give you 2r cubed sine theta, and then this is minus r cosine theta, and then all of that multiplied by r, and then dr d theta. Ouch. Okay, so probably should distribute the r in. And so this is negative 2r cubed cosine theta sine theta minus 2r squared sine theta plus 2r to the fourth sine theta minus r squared cosine theta dr d theta. Okay, so now we can integrate with respect to r, and we can imagine doing two things at once, I suppose, or maybe not. Maybe that's not a good idea, because this would be minus r to the fourth over 2 cosine theta sine theta, and this would be 2r to the third over 3 sine theta. This is 2r to the fifth over 5 sine theta, and then this is r cubed over 3 cosine theta. And then r goes from 0 to 1. Okay, so just plug in r equals 1, and that gives you negative 1/2 cosine theta sine theta minus 2/3 sine theta plus 2/5 sine theta minus 1/3 cosine theta d theta. Yeah, this is just like the tedious integration part. So you integrate this with respect to theta, and that's going to give you negative sine squared theta over 4. And then integrating this with respect to theta gives you plus 2/3 cosine theta. And that one gives you minus 2/5 cosine theta. And this one, it gives you minus 1/3 sine theta. From 0 to pi over 2. So plug in a pi over 2. This is 1, so that's minus 1/4. Plug in pi over 2 here, that's 0. And let's do each of these individually. Okay, so if you subtract and plug in a 0, that's 0. This one is going to be 0 minus 2/3 for the lower part. This one is going to be 0 minus a negative 2/5. That's plus 2/5. And then this one's going to be minus 1/3. Okay, and you add all those together, and that's negative 17 over 20.